All right, let's go.
Number 7. MACHOs, the candidate that needed no new physics at all, ruled out anyway. Part 1 covered the exotic particle candidates. This one is different. It required no new physics whatsoever. In the 1980s, before axions and WIMPs dominated the conversation, a simpler idea seemed entirely plausible. What if dark matter was not some undiscovered particle, but ordinary matter that was simply too dim to see? Massive compact halo objects, MACHOs, a category covering faint brown dwarfs too small to ignite fusion, isolated black holes, neutron stars, and old white dwarfs drifting through the galactic halo invisible not because of exotic physics, but simply because they emit too little light to detect directly. The proposed detection method was elegant: gravitational microlensing. If enough MACHOs exist scattered through the halo of the Milky Way, one should occasionally pass directly in front of a distant background star as seen from Earth, and its gravity should briefly focus and brighten that star's light in a distinctive, predictable pattern. Large survey projects, including the MACHO project and EROS, monitored millions of stars in the Large Magellanic Cloud throughout the 1990s specifically to catch this signature. They found some events, just nowhere near enough. The observed microlensing rate ruled out MACHOs as making up more than roughly 20% of the dark matter in the galactic halo, and combined follow-up work using Hubble Space Telescope data further constrained low-mass stars to account for at most a few percent of the total. The conclusion, reached by the early 2000s and essentially unchanged since, was direct. Ordinary, dim, unlit matter simply is not abundant enough to explain the missing mass of the universe. Whatever dark matter is, it has to be something genuinely new. Number 6. Self-interacting dark matter. Dark matter that bumps into itself, just never into you. Standard cold dark matter models assume dark matter particles interact with each other and with ordinary matter only through gravity. This simple assumption works remarkably well at describing the largest structures in a universe. But at smaller scales, inside individual galaxies, it runs into real, persistent problems. Simulations built on purely gravitational dark matter consistently predict galactic cores that are far denser and more sharply peaked than what astronomers actually observe. They also predict many more small satellite galaxies orbiting large galaxies like the Milky Way than have ever actually been found. Self-interacting dark matter, or SIDM, proposes a specific fix. Dark matter particles do interact with each other, colliding, scattering, exchanging momentum through some entirely new force that only affects the dark sector, leaving ordinary matter completely untouched. This self-interaction would smooth out and soften the dense central cores that pure cold dark matter predicts, bringing simulations into much closer agreement with what telescopes actually see. The theory gained significant new momentum in April 2026 when physicist Haibo Yu at UC Riverside published a study in Physical Review Letters proposing that dense, gravothermally collapsed clumps of self-interacting dark matter, each with a mass around 1,000,000 times that of the Sun, could simultaneously explain 3 separate and previously unconnected astronomical puzzles observed in gravitational lenses, in disrupted stellar streams, and in the unusual behavior of small satellite galaxies. A separate paper published in January 2026 used new numerical simulation techniques to model, for the first time in detail, exactly how these self-interacting dark matter halos undergo a dramatic, late-stage gravothermal collapse, heating up and contracting instead of simply spreading out, a genuinely novel and only recently well-modeled prediction. SIDM remains unconfirmed, but it is currently one of the most actively pursued alternatives to the standard cold dark matter picture. Number 5. Fuzzy dark matter. Dark matter so light it behaves like a wave of the size of a galaxy. This candidate takes the axion concept from part 1 and pushes it to its most extreme possible limit. Fuzzy dark matter proposes an ultralight boson with a mass around 10 to the minus 22 electron volts. a mass so extraordinarily small that quantum mechanics forces the particle to behave less like a discrete point and more like a spread-out wave, with a de Broglie wavelength potentially large enough to span an entire galaxy. At this scale, dark matter stops behaving like a swarm of individual billiard ball particles entirely. It behaves like a single, continuous, coherent quantum wave. This produces genuinely distinctive predictions that differ from every other candidate on either list. Because the wave nature of the particle prevents it from clustering below a certain minimum scale, fuzzy dark matter halos should exhibit a dense, stable, wave-like core at their center, sometimes called a soliton core, surrounded by a granular interference pattern rather than the smooth distribution that standard cold dark matter predicts. Researchers have used the observed properties of ultra-faint dwarf galaxies, including Eridanus II, and detailed analysis of the Lyman alpha forest, the pattern of light absorption from distant quasars passing through intervening gas, to place increasingly tight constraints on exactly how light this particle could be, work that has continued to be refined through comprehensive review papers published as recently as mid-2025. No detection has been confirmed, but the wave-like signature fuzzy dark matter predicts is different enough from every other candidate that a confirmed detection would be immediately and unambiguously distinguishable. Number 4. Mirror matter, a parallel copy of everything that only touches us through gravity. This is one of the oldest hypothetical matter proposals still under active, serious investigation, and one of the strangest. The idea traces back to 1966, when physicists I.U. Kobzarev, L.B. Okun, and I.A. Pomeranchuk built on earlier work by Nobel laureates T.D. Lee and C.N. Yang to propose something genuinely radical: a complete mirror copy of the entire standard model of particle physics, mirror quarks, mirror electrons, mirror photons, bound together by their own mirror versions of the strong, weak, and electromagnetic forces coexisting with our own universe, invisible to us specifically because the only force connecting the two sectors is gravity. Under this theory, mirror matter would form its own mirror atoms, mirror stars, potentially even mirror planets, all completely invisible and undetectable through any conventional telescope, because mirror photons are not the same as ordinary photons and cannot be seen by ordinary detectors. The only trace mirror matter would leave in our universe is gravitational. Interest in mirror matter surged again in August 2025 when researchers at UC Santa Cruz published a specific and testable version of the theory, proposing that in the extreme heat and density of the very early universe, a hidden mirror sector could have collapsed directly into dense, black hole-like objects, which then constitute all of the dark matter observed today, offering a specific formation mechanism the original 1966 proposal never addressed. Separately, cosmological data on the primordial abundance of helium has already placed significant constraints on any dark sector evolving in perfect lockstep symmetry with ours, meaning a fully symmetric mirror universe is largely ruled out, but asymmetric versions, where the mirror sector evolved differently after some early symmetry-breaking event, remain a genuinely open and actively studied possibility. Number 3. Dark photons. A hidden force of nature that might explain why we cannot see dark matter directly. Every force in the standard model has a carrier particle. Electromagnetism has the photon. The strong force has the gluon. The weak force has the W and Z bosons. Dark photons propose that the dark sector, whatever collection of particles actually makes up dark matter, has its own force carrier too. A particle that behaves almost exactly like an ordinary photon, but belongs entirely to a hidden sector, interacting with ordinary matter in light only through an extremely weak process called kinetic mixing. This is a genuinely different kind of hypothesis from the WIMP or the axion. It does not just propose a new dark matter particle, it proposes an entirely new force of nature, largely or completely hidden from every experiment physicists have run to date, that could explain both what dark matter is and why it has been so persistently difficult to detect directly. The search strategy is correspondingly different too. Rather than waiting for a dark photon to strike a detector directly, physicists at facilities including DESY in Germany and Jefferson Lab in the United States run light shining through a wall experiments, firing an intense laser at an opaque barrier and checking with extraordinarily sensitive equipment on the other side for any trace of light that could only have passed through by briefly converting into a dark photon and back again. Other experiments, including one proposed at the Yemilab Underground Laboratory in Korea, search for dark photons produced when a high-energy electron beam strikes a dense target. No confirmed dark photon has been detected by any method, but 2023 and 2024 research from the University of Adelaide's Center of Excellence for Dark Matter Particle Physics has continued refining exactly how a dark photon could serve as what researchers call a portal, a genuine physical bridge connecting the ordinary visible universe to whatever the dark sector actually is. Number 2. Preons, the idea that quarks and electrons are not actually fundamental at all. Every particle covered so far in both this video and the one before it is proposed as a new addition to the roster of fundamental particles. Preons propose something more radical, that some of the particles we already consider fundamental, quarks and leptons, including the electron itself, are not fundamental at all and instead built from smaller, even more basic constituent particles. The motivation is a genuine pattern that the Standard Model describes perfectly but does not explain. Quarks and leptons come in 3 near-identical generations, each one simply a heavier, unstable copy of the one before it, differing from each other only in mass. The electron, the muon, and the tau particle are functionally identical in every measurable property except mass instability. The Standard Model has no built-in explanation for why this repeating pattern exists, or why there are exactly 3 generations rather than 1, or 5, or an infinite number. Preon models, developed independently by several physicists beginning in the late 1970s, most notably Jogesh Pati and Abdus Salam, propose that quarks and leptons are composite particles built from a small number of truly fundamental preons, in roughly the same way that protons and neutrons are themselves built from quarks. Under this framework, the 3 generations of particles would simply reflect different possible combinations or excited energy states of the same small handful of preons, offering a genuine explanation for the repeating pattern rather than treating it as an unexplained input to the theory. No experimental evidence for preons has ever been found. Every high-energy collision experiment ever run, including decades of data from the Large Hadron Collider, continues to show quarks and electrons behaving as genuinely point-like, structureless particles, with no evidence of internal substructure down to distances smaller than roughly 10 to the negative 19 meters. The theoretical elegance of preons remains completely unmatched by any experimental support. Number 1. Hot dark matter. The discovery that might overturn a core assumption everyone has made for decades. Every candidate discussed across both of these videos has shared one quiet, largely unquestioned assumption, that dark matter is cold, meaning that whatever it is, it was moving slowly relative to the speed of light when it decoupled from the rest of the universe in the extremely early cosmos, a property essential to the standard cold dark matter model that has successfully explained the large-scale structure of the universe for decades. In January 2026, new research proposed something that directly challenges that foundational assumption. Rather than being born cold and sluggish, dark matter particles could have been produced in a genuinely hot state, moving at speeds close to the speed of light in the earliest moments of the universe, only cooling and slowing down significantly later. This is not a minor technical adjustment. The temperature of dark matter at the moment of its formation directly determines how it clusters and how cosmic structure subsequently forms around it. A hot origin would produce measurably different patterns in the distribution of galaxies and in the fine details of the cosmic microwave background than the cold dark matter model has assumed and successfully used for decades. If confirmed, this would not just add one more item to the list of candidate particles. It would mean physicists have been assuming the wrong starting temperature for the entire dark matter framework since the theory was first developed, requiring a genuine revision to how structure formation itself is modeled. As of 2026, this remains a new and actively debated proposal, not yet settled consensus. It is included here specifically because it demonstrates something important about the entire two-part search this series has covered. Even the most basic, seemingly settled assumption underlying every single candidate discussed, cold, slow, gravitationally clumping dark matter, is still being actively questioned, tested, and potentially overturned in papers being published right now.
7 more forms of hypothetical matter. MACHOs, the candidate that needed no new physics at all, tested directly through gravitational microlensing and ruled out by the early 2000s. Self-interacting dark matter, gaining serious new momentum in 2026 by potentially solving 3 separate astrophysical puzzles at once. Fuzzy dark matter, so light it behaves as a single wave the size of a galaxy. Mirror matter, a complete parallel copy of the entire standard model connected to our own universe by nothing but gravity, with a new formation mechanism proposed in 2025. Dark photons, an entirely hidden force of nature that might explain both what dark matter is and why it has been so difficult to find. Preons, the radical proposal that quarks and electrons themselves are not truly fundamental. And hot dark matter, a genuinely new 2026 challenge to the coldest, most basic assumption the entire search has rested on for decades. Combined with everything covered in Part 1, WIMPs, axions, sterile neutrinos, primordial black holes, strange quark matter, magnetic monopoles, Q-balls, antimatter, and exotic negative energy matter, that is 15 entirely different, seriously proposed answers to the question of what fills roughly 95% of the universe. Not one of them has been confirmed. All of them are still being searched for, right now, in laboratories, telescopes, and detectors on every continent, simultaneously. Subscribe to Cosmic Hives. See you in the next one.